Right, so today we are going to be looking at a new section, 7.2, called Integration by Substitution. This picture is Martin Luther King Jr.'s birthplace. Get it? Integration, so I think that they picked that on purpose. You guys know that for derivatives, when we use the chain rule, it allows us to differentiate a wide variety of functions, but we are able to find antiderivatives for only a limited range of functions. We can sometimes use substitution to rewrite functions in a form that we can integrate. So we had some problems where I told you we kind of were doing a little bit of guessing and checking. Well, this integration by substitution is going to allow us to not just do guessing and checking. So, for example, the first one here, the integral of x plus 2 quantity squared raised to the 5th power. What we're going to do is we're going to let u equal x plus 2. And a lot of times it will be, you'll have like an inside function and an outside function. So notice that x plus 2 is the inside function. So a lot of times it will work that way. Then you know that, and I'm going to kind of write this, add something on here a little bit. If u equals x plus 2, then you know that du dx equals 1, and that's where they get this du equals dx, because you split the du and the dx, remember, when it's convenient to do so. So a lot of times on these slides they won't show that, so I'll try and show that for you. So then you're going to replace the x plus 2 with a u instead. So we get the integral of u to the 5th du. And you have to remember that whenever you are doing substitution, the variable of integration, whatever variable, has to match the variable in the expression. So the du, you can't have u to the 5th dx. If you're going to have a u, it has to be a du. So you have to make sure that those things match. So then we do the antiderivative, so we raise the power by 1, so we get u to the 6, divide by the new power, so plus some constant. And then what you want to make sure, don't forget to substitute the value for u back into the problem. So remember, it wasn't really a u, it was an x plus 2, so you would substitute it back in, and then you would have your answer. So that is an example of using u substitution. Okay, here's another one. This may or may not be the exploration one in your current book because it might be from the older edition. That doesn't matter. So we've got kind of an expression. We've got an x squared underneath this radical. We have an x out here, so it's not just a constant. So this one could be a problem for us. So one of the clues that you look for in order to, when you do the u substitution, is you are looking for a function that's inside here somewhere that the derivative is also there. For example, notice the function 1 plus x squared. What's the derivative of 1 plus x squared? Well, it's 2x, and there's a 2x right there. So that's what you're trying to look for when you are trying to set up a problem like this. So the derivative of 1 plus x squared is 2x dx. And so then we're going to let u equal 1 plus x squared. Then du, and again, keep in mind that the part they're not really showing is, oops, have to get the pen first. Right here is we have du dx for this right here would equal 2x, and then they take it to this. So kind of keep that in mind. All right, so back over here, then 1 plus x squared is u, so remember the square root, so that's u to the 1/2. And then we just got done saying that du is the same as 2x dx, so you are substituting in place of the 2x dx, you're putting a du. So we have u to the 1/2 du, and we're going to do that integral, which we can do because it's just the power rule in reverse. So we raise the power by 1, divide by the new power. When you divide by 3/2, same as multiplying by 2/3, and then plus a constant. So, and then again, remember, it's not a u, it's really a 1 plus x squared, so you have to put the 1 plus x squared back, and now you have your answer for the integral. Okay, so that's the idea. So again, trying to locate what function do I have here that I also have the derivative in the function. So this only worked because of the 2x in the original, and there are a lot of integrals that cannot be done by substitution. This is just one method for certain kinds of problems. There are other types of integration problems that you can't use this method. It doesn't fix everything. All right, here's another one. So if you let u equal 4x minus 1, then we get du dx would equal 4, so then du equals 4 dx. I don't have a 4, I just have a dx, I don't have a 4. So what we can do is we want to solve for dx, because I want to be able to substitute the dx for something in terms of du. So I have to solve this for dx by dividing by 4. So now I know that dx equals 1/4 du. I'll be able to substitute a 1/4 du in place of the dx. So now we have u to the 1/2, because it's the square root of u, so u to the 1/2 times 1/4 du. Now I would bring the 1/4 out front. I'm not sure if they do that here. No, they didn't do that here. I probably would, so let me just kind of show you that. Whoops, oh, I think I could just hit the pin. So if you take that out front, 1/4, the integral u to the 1/2 du, and then you can do 1/4 times, you're still going to have this u to the 3/2, and then you're going to have a 2/3 here. So is this saving anything? Probably not, because we're not, I'm thinking that it's a definite integral and I was going to go on, but no, I probably wouldn't do that. So I'm going to go on, because you can actually take the 1/4 and multiply it by the 2/3 and get 1/6. But in my mind, I was used to doing the definite integrals that we've just got done doing, and I'm setting it up to make it easier to do the math, but this actually is done. Except that we have to always remember to replace the u with what it really was originally. Okay, so for this next one, now when you are choosing what the function is, it can't be cosine, because if you let cosine be your u, then you would need to have sine somewhere in the problem, and we don't. So, so you want to kind of keep that in mind when you're picking something out. But if we let u equal 7x plus 5, then we get du dx equals 7, so that means du equals 7 dx. But again, I don't have a 7 over there, so I'm going to rewrite this. I'm going to divide both sides by 7 and get 1/7 du equals dx. And now I can make my substitution. I've got the integral of cosine u times 1/7 du. We know the antiderivative of cosine is sine, because the derivative of sine is cosine. So we know we're going to end up with that. So we have sine u times 1/7. Don't forget your plus a constant. So that's taking the antiderivative. And then remember, it wasn't really a u, it was a 7x plus 5. So you have to put it back. And then that would be your answer. Okay, here's another example. Now, notice, because you got a lot of stuff going on here, but remember to focus on, I'm looking for a function that the derivative is also there. So the derivative of x cubed is 3x squared, and I have an x squared out here. So that's your hint on what you want to use for u. So we're going to let u equal x cubed. Then we get du dx is going to be 3x squared, which means du is 3x squared dx. So notice I have an x squared dx, but I don't have a 3. So I'm going to divide both sides by 3. I want to have x squared dx, because that's what I see right here, x squared dx, because we can change the order of multiplication. So now I'm going to replace the x squared dx with a 1/3 du, replace the x cubed with a u. And we get 1/3. This time they did pull the 1/3 out front. The integral of sine u du. The antiderivative of sine is going to be negative cosine. So we get this answer. And then you just have to put back the x cubed, and you're done. Don't forget your plus c, because we're doing indefinite integrals, so we definitely need to have a plus c. All right, so for this next one, now I have a sine and a cosine here. Well, we know the derivative of sine is cosine, but we also know the derivative of cosine is negative sine. So you might wonder, well, could I go either way? Well, except that this is not just sine. It's sine x and then that whole thing raised to the 4th power. So you're going to want to let u equal the sine x, because then cosine x is going to involve the du. So if we start, because remember, sine to the fourth x means this. So if you let u equal sine x, then you have du equals cosine x dx. So now we can substitute, and we get the integral of u to the fourth du, which, you look at what you started with and it looks complicated. You look at this and it's easy. So we get u to the fifth over 5 plus a constant, and then you just plug back in what u was equal to, and you're done. Okay, now notice that this one is not, this is a definite integral. We have from 0 to pi over 4. So this is different. We're still going to solve this by using substitution, and pay attention to some of the things that's going to make this one a little bit easier. So I know that the derivative of tangent x is secant squared x, so I would let u equal tangent x. A little different technique. But we're still going to let u equal tangent x. So then the derivative is going to be secant squared x dx. Because remember, this again is du dx equals secant squared x. They split the variables. So now we see that we have this information. Now, here's what we have to do though. I can't just, because I'm changing the function and I'm going to be rewriting it as u du, my limits of integration are going to change as well. So what we're going to do is we're going to find new limits first and rewrite the integrand with new limit, or the integral with new limits, and then we don't have to go back and substitute. So if I plug the lower limit into u, plug a 0 in, and I do tangent of 0, I get 0. So my lower limit is going to remain a 0. If I plug in the upper limit, which is pi over 4, into my function for u, so tangent of pi over 4 equals 1, so my upper limit is going to become a 1. So I'm going to replace my limits of integration with new limits of integration based on this. So now when I do the antiderivative, and I get u squared over 2, plug in a 1, plug in a 0, and we get our answer of 1/2, and it's just way easier. Now, the alternative is to not put limits on at all, leave it the u du, and then put the tangent x back in and evaluate it with the old limits. So that's your option, but I recommend finding new limits. So here it is with the original limits. If you did it that way, you don't do this. Okay, don't do that. That is like a no-no. That would be wrong. Your limits were for x, not for u, so you can't use those. So leave them off and then work it out. And then after you put back the tangent x in place of the u, then put your original limits in, and you can evaluate. But you can kind of see it looks a little messier. It's kind of easier just to take care of it at the beginning. Okay, here's another one. Again, after a while you start to recognize things, like right away I see, oh, if I take the derivative of x cubed, I'm going to get 3x squared, so this should be u. So I'm going to let u be x cubed plus 1. And then du is 3x squared dx, and we've got everything in place. Going to find new limits. So we plug in a -1, and we get 0. And we plug in a 1, I'm plugging it in right here, so 1 cubed plus 2 is plus 1 is 2. And so we put our new limits. This is u to the 1/2 du. Do your antiderivative, and now you're using your new limits, and when you plug those in, you can get your answer. Okay? In another generation or so, we might be able to use the calculator to find all integrals. Right now, computers, there's a ton. When you guys take a calculus class in college, you'll see that you do a lot of, this is basic math, basically. When you go on and take calculus in college and you take some differential equation classes and upper level classes, those of you who are wanting to be engineers and mathematicians, you're going to find that this kind of stuff is like basic math, but a lot of it is done on with computer software. Until then, remember, half of the AP exam, actually a little more than half now, and half the nation's college professors do not allow calculators. Sometimes they'll allow calculators, but not graphing calculators. So you have to know some stuff about integrals. So you've got to practice finding integrals by hand until you are good at it. So that is it for today. Your assignment, you're going to have some review problems to do from like the quick review, and then I will do probably some examples from the textbook tomorrow, and you'll have an assignment then.